Hi everyone. We're going to begin our last little mini unit on decimals by looking at one category of decimals, terminating decimals. For decimals, there's actually three categories. The first one is called terminating, and terminating decimals are decimals that terminate, that include a finite number of non-zero digits after the decimal point. So 0.5 is a terminating decimal. 0.2168 is a terminating decimal. If the number of decimals after the decimal point, if the number of digits rather after the decimal point is finite, it ends, then it's called terminating decimal. The next category of decimals is called repeating decimals. And these are not terminating, so they go on infinitely long, but they have a repeating pattern of digits of finite length. So 0.2 repeating. So that would be 0.222 on and on and on. 0.264 with, say, the 64 repeating would be 0.264, 64, and so on. All right. The last category of decimals is the other category. So if it's not a repeating decimal and it's not a terminating decimal, then it's simply called non-repeating, non-terminating. You can actually find some patterns like this. You can say, well, how about 0.1 and then 0, 1, so 1, 0, then 0, 0, 1, so 2 zeros, 0, 0, 0, 1, and so forth. All right, so those are a special class of decimals, and they are something that we probably will not talk about in this class, but they lead to something called irrational numbers. All right, so in focusing on terminating decimals, there's actually 4 claims that I want to make, and these are 4 facts about these. The first fact is that all terminating decimals can be expressed as a rational number, and rational numbers are essentially rational, the root word is ratio, are numbers of the form a over b, where a and b are integers. All right, and so all terminating decimals can be expressed as rational numbers with a over b, where b is some power of 10. So the first example of that is at 1.215. So what fraction does that represent? So what you can do is expand that. 1.215 is 1 plus 2 tenths plus 1/100th plus 5 thousandths using the place values of decimals. Write those all over a common denominator, say 1,000. So 1 becomes 1,000 over 1,000. The 0.2, 2 tenths, becomes 200 over 1,000. The 1/100th becomes 10 over 1,000, and 5 thousandths just remains that. Add those all together, and you get 1,215 over 1,000. Now, of course, you can simplify that, but the claim is that any decimal that terminates can be written as a fraction over some power of 10. In this case, it's over the power 10 to the third. Claim number 2 about terminating decimals is that all fractions, so it's basically the opposite of claim 1, all fractions, a over b, where b is written is some power of 10, can be written as terminating decimals. So in claim 1 we said all terminating decimals can be written as a fraction where the denominators are power of 10. This is just the reverse. All fractions with a power of 10 in the denominator can be expressed as terminating decimals. So here's an example. 817 over 10,000. What you can do again is write the numerator in expanded form. That's 800 over 10,000 plus 10 over 10,000 plus 7 over 10,000, and then reduce. So 800 over 10,000, if I reduce, since you divide the top and bottom by 100 is 8 over 100. 10 over 10,000 is 1 over 1,000. 7 over 10,000, well, you can't reduce that anymore. So now I have my places, the hundredths, the thousandths, and the 10,000ths. So 817 over 10,000 is going to be 0. There's no tenths. 800ths, 1,000th, and 7 10,000ths. So this decimal written over a power of 10 can be written as a terminating, this fraction rather, written over a power of 10 can be written as a terminating decimal. Claim number 3 is that all rational numbers, all fractions of the form a over b, where, and this is the key to the claim, where b is just written as a power of 2 times some power of 5. So a fraction that can be written entirely with a denominator composed of 2's and 5's can be expressed as a terminating decimal. And now I'm going to put you in your teacher role. Remember Pesky? Pesky is that student in our class that always asks why. Well, let's delve into this just a little bit. When Pesky asked why, what's special about those 2's and 5's? Here's what you can say. You can say we're going to use equivalent fractions to express the number, the rational number, as another fraction with a denominator that's a power of 10. And then we're just going to use claim number 2. Okay, so to use this, to do this, to sort of prove that this is true, we've got to use the fact that the power of 10, so 10 to some power, 10 to the c, I'll call it, is equal to 2 to the c times 5 to the c. Okay, so maybe you're skeptical. But what does that show us? Okay, let's look at a couple examples. I've got the number 11/8. 11/8, okay, that is 11 over 8. It can be written as 2 times 2 times 2, or 2 cubed. So I've got 11 over 2 cubed. The denominator is, if it's only composed of 2's or 5's, and sometimes both. So this is 2 cubed. Now I'm going to use the fact, okay, 2 cubed, I want to convert it into a power of 10. What if I multiply the top and the bottom by 5 cubed? So the top becomes 11 times 5 cubed, and 5 cubed is 125. That becomes 1375. 2 cubed times 5 cubed is actually 10 cubed. But 10 cubed is 1,000. So I've taken this fraction, 11 over 8, and I've written it as a fraction over a power of 10. And now, using what we did in the earlier claims, we know that's just 1.375. Okay? How about 27 over 160? Doesn't quite look like it would be written over a power of 10's or 5's and 2's. But let's factor that bottom. Okay, so 160 is 32 times 5. But 32 is 2 to the 5th. So 27 over 160 is 27 over 2 to the 5th times 5. Okay, I want to get this written over a power of 10. So I've got 2 to the 5th. I've got 1 5. I'm going to multiply the top and bottom. This is the equivalent fraction part right there, by 5 to the 4th. And 5 to the 4th is 25 times 25 is 625. So when I do that, I get on the top, I'll get 27 times 5 to the 4th, which is 16,875. But on the bottom, I get 2 to the 5th. 5 times 5 to the 4th is 5 to the 5th. 2 to the 5th times 5 to the 5th is 10 to the 5th. And 10 to the 5th is 100,000. So this, I've now converted the number 160 to some power of 10 using equivalent fractions. That's the decimal 0.16875. So again, the denominator composed of 2's and 5's can be written as a terminating decimal. Our last claim, claim number 4, is that any number that can be written, any rational number, so it can be written as a form A over B, and it's important here in lowest terms, where it's reduced, where A and B are integers, with B is composed of some primes other than 2's and 5's. It can have 2's and 5's, but it also has something else. Those decimals, those fractions rather, cannot be expressed as terminating decimals. So let's take a look. 23 over 28. That's 23. 28 is 4 times 7, which is 2 squared times 7. I can't reduce it at all. Okay, 23 is prime. It's 23 times 1. So that denominator has something other than a 2 or a 5, which means it could not be expressed as a terminating decimal. How about 33 over 75? Okay, 75 is 3 times 25. But take a look at the top. The top, 33, is 3 times 11. Okay, so I've got 3 times 11, 3 times essentially 25, or 5 squared. But these 3's can be canceled. So 33 over 75 is actually equivalent to 11 over 5 squared. That fraction is composed entirely of a 5 in the denominator, so that one actually could be expressed as a terminating decimal. So it's only when your fraction has some denominator, some prime other than 2's and 5's, where it's been written in lowest terms, those fractions cannot be written as terminating decimals.